students, welcome to day 29 of PU2 Brahmastra Series, and in today's class we are going to discuss a very important topic, that is electrochemistry. Okay, so in this lecture I have discussed almost 60 plus questions, which includes both theory and numerical questions, also your MCQ type questions. So if you watch this one video and practice all the questions, then I can guarantee you that you can able to attempt all the questions that will be asked in your PU2 examinations. So make sure please sit with a notebook and a pen, note down the questions, write the answers, check whether you know the answers or not. If not, you can see the solutions and write down the answers. Okay, after that you have to prepare these questions. So now let's get started without any further delay. Okay, coming to the weightage, so according to the blueprint, this chapter carries 13 marks. Okay, how this 13 marks is distributed? You will get one MCQ question, okay, and there are 4 3-marker questions. In this also, 2 3-marker questions will be of theory type and 2 3-marker questions will be of numerical type, right? So we will get total 13 marks from this particular chapter. Clear? Now coming to in this particular class, what you will be getting almost 55 plus 10, 65 questions from this one particular chapter. So just imagine, from this chapter 4 questions are going to come, and if you have practiced 60 questions, so that 4 questions will definitely be from this 60 questions, right? I can guarantee you that. So make sure that you watch this video completely, understand each and every question and attempt them, try to answer them. If you do not know the answer, understand the explanation, write down the answer and then mark those questions which you were not able to attempt. Okay, fine. Okay, here I want to make an announcement regarding the PU2 Success Blueprint Test Series. So this is a test series launched by Diksha to help you to get 95% and above in your PU2 examination, right? So this test series includes 12 mock tests in which there are 4 part tests and 8 full-length paper, and the first test of this test series will be released on December 15th. Okay, so please remember this date. And apart from the test, the question papers are definitely on the basis of the latest syllabus and pattern. You will be getting one-shot revision videos. You will also be getting the solution videos with detailed explanation and doubt clarifications of all the question papers will be done. Okay, and all this you can avail at a discounted price of 599 rupees only. So students, if you are if you are going to appear in your PU2 examinations and you want to ensure that you will get 95% and above, so please do not miss this opportunity. Go to the description section, registration link is there, click on it, buy this test series because the first test is released on 15th of December. Okay, so please do not delay and purchase it as soon as possible. Okay, let us now continue with our syllabus or with our class today. So first I want to give some formulas to revise, because this chapter has many complicated or many difficult formulas I can tell. So I want to give you a glimpse of that first. So this one, E of the cell is equal to E of cathode minus E of anode. So that is what to calculate E naught of a cell. Next, Nernst equation, E of the cell is equal to E naught of the cell minus 0.059 n log of product concentration by reactant concentration. Please remember, this is always product by reactant. Okay. Next, delta G is equal to minus NF E naught of the cell. Delta G is equal to minus 2.303 RT log K. Okay. And next we have at equilibrium. Okay, at equilibrium what happens? This Nernst equation, right, E of the cell becomes 0. So that means E naught of the cell will be equal to plus 0.059 by n log K. Okay, so when at equilibrium this part is equal to K. Okay, so that is what I have substituted here. Okay. Next, there are, when you talk about the conductivity, okay, so there are different definitions which are very confusing, so we will revise them once. So the first term that you should remember is resistance. Okay, resistance symbol is R. It is something which opposes the flow of current. Its unit is ohm or OHM. The next one is resistivity, rho. Okay, The resistivity for a substance is its resistance when it is 1 meter long and its area of cross section is 1 meter square. So any substance which is 1 meter long and has a cross sectional area of 1 meter square, whatever resistance is provided by this particular substance of 1 meter long and 1 meter square area, that resistance is called as resistivity, and its unit is ohm meter or ohm centimeter. Okay. Next, coming to conductance. Conductance is the opposite of resistance or inverse of resistance, and the formula is ohm inverse, or we write it, ohm inverse is written as S for Siemens. Next we have conductivity. Conductivity is the opposite of resistivity. Okay. It is the conduction of electrolyte per unit volume. So one electrolyte in 1 unit of volume, how much it can conduct electricity, that is called as conductivity, and its unit is just the opposite of resistivity. So here you should remember it is also 1 by rho, right? So ohm meter, so it will be ohm inverse meter inverse, and for ohm inverse I can write S, so S meter inverse or S centimeter inverse. Next term is cell constant. Cell constant is written by G star, and its formula I can write down here, it is L by A, okay, length by area. So meter by meter square, so the unit will be meter inverse or centimeter inverse. Next we have molar conductance. Formula is lambda m. So it is conductance of all the ions produced by 1 mole of an electrolyte in a specific volume of solution. So if you have taken 1 mole of an electrolyte, in that cations will be there, anions will be there. So the total conductivity because of the cations and anions for 1 mole of electrolyte is called as your molar conductance. Unit is S meter square mole inverse or S centimeter square mole inverse. Okay, fine. Now let us recapitulate the formulas of Faraday's law. According to Faraday's law, M is equal to ZIT, where Z is electrochemical equivalent and it is equal to molar mass divided by N into 96500. Okay. Next, if you see Faraday's second law, it is M1 by M2 is equal to E1 by E2. Next, resistance formula, R is equal to rho L by A. Here rho is resistivity, L length and A area. Resistivity, just you can arrange this one, you will get rho is equal to RA by L. Okay. Cell constant is L by A, just now we discussed, right? And next, coming to conductance. Conductance is what? Resistance opposite, so that is 1 by R, or it is represented by G. Then you have conductivity. Conductivity is the opposite of rho, so that is equal to 1 by rho. So I can write L by RA, right? Just the reverse of this one. Next you have molar conductivity. Molar conductivity formula is kappa into 1000 by C, where C is concentration. Okay, fine. Now products of electrolysis, this is also from where questions can be asked. So you should remember, for molten NaCl you have at cathode Na metal is generated and chlorine at anode. For aqueous NaCl, H2 at cathode and Cl2 at anode. These two reactions for molten NaCl and aqueous NaCl is very, very important. Similarly, you can see for dilute H2SO4, you will get H2 at cathode, O2 at anode, and for concentrated H2SO4, same H2 at cathode and S2O8, 2 minus at anode. Okay. Next, we will do some VSA questions now. The EMF of hydrogen electrode in terms of pH is, okay. So now, if you see the reaction of hydrogen electrode, it is H plus 1 electron gives you half H2, right? So now if I write E of the cell is equal to E naught of the cell minus 0.059, okay, by 1 log of H2 by H plus, okay. Now this is half. Now you can see 1 atm pressure means H2 pressure is 1 atm. So I have written the Nernst equation. In the Nernst equation, this is 1 atm, so I can write this one as E of the cell, E naught of the cell is 0 for hydrogen electrode, right? So remember, for hydrogen electrode, okay, E of the cell is equal to 0. So what I will get here, E of the cell is 0, so I can write E naught of the cell is 0, okay. So I can write E is equal to, this is 0 minus 0.059, okay, then log of, this is 1, H plus to the power of minus 1. Okay, so I can take this minus into the towards the starting. Okay, minus log of H plus. Okay, can you see this? Okay, now minus log of H plus is nothing but pH, so I can write minus 0.059 into pH, right? So that option, I think option number D is the correct answer here. Okay, next question. E0 values of Mg, zinc and iron is given to you. Which of the statement is correct? Okay, so Mg2 plus zinc is Mg2 plus to Mg value is minus 2.37. Okay, so I have Mg2 plus to Mg is equal to minus 2.37 volt. Then you have Zn2 plus to Zn, okay, minus 0.76 volt. Fe2 plus to Fe, okay, that is minus 0.44 volt. Now if you see here, this is having the least reduction potential, right? Reduction potential is least means it doesn't want to get, it has more tendency to get oxidized, right? So it will be a very good reducing agent, right? And this one will be a very good, now see, this one is having the lowest, this one is having the highest reduction potential, okay, because a negative number, you know, less is the number, more is the value, minus 2 is less than minus 1, right? So I can say this is having the least, this is having the highest reduction potential. That means, so let me write the order, reduction potential order is Fe highest, then you have zinc and then you have manganese. Now reduction potential, the one which is undergoing reduction will also be behaving as a very good oxidizing agent. So I can say that oxidizing agent order is also like this, Fe and Zn and magnesium, right? So that means what? So Fe can oxidize zinc and magnesium, zinc can oxidize magnesium, right? So now if we see the statements given, Zn2 plus will reduce Fe2 plus. So now see, Fe can oxidize zinc, that means zinc can reduce Fe. So this statement can be correct. Next, zinc will reduce magnesium, no. Oxidizing agent means zinc will oxidize magnesium. So this is wrong. Then Mg will oxidize Fe, no. Mg can reduce Fe. Fe can oxidize Mg, but Mg will reduce Fe. So this is also incorrect. Zn will oxidize Fe, no. Zn will reduce Fe. Fe will oxidize Zn. So this is also incorrect. The correct statement is option number A. So I can say now that Fe can oxidize zinc and magnesium, okay, and zinc can oxidize magnesium, right? Now if I talk in terms of reducing, okay, Mg can reduce, okay, zinc and Fe, and Fe can reduce, zinc can reduce Fe. Okay, so now you can see the statements once again. Zinc will reduce Fe, yes, that is correct. Zinc will reduce Mg, have we written that statement? No. Mg oxidizes Fe, have we written this one? No. Mg can reduce zinc and Fe, right? So Zn oxidizes Fe, Zn can oxidize magnesium but not Fe, okay. So that is why first statement is correct, okay. Next question. The standard reduction potentials have been given, the strongest reducing agent is. So this one you should remember that if strongest, please note down this one, if strongest reducing agent is asked, means what? It will reduce others, itself it will undergo oxidation, and for going oxidation the reduction potential value should be low, okay. So strongest reducing agent means itself it undergoes oxidation, right? So for oxidation what you should see, the E0 reduction value should be low, okay. So now you can see here, this is minus 0.76, this is minus 0.74, this is plus, right? So here you see this is the least one. So zinc will be the correct answer. Option number A is the correct answer here. Okay. Next question number 4. The reaction which is taking place in nickel cadmium battery can be represented by which of the following equation? So this is from the batteries. So nickel acts as a anode there, right? So nickel will get oxidized. So the reaction is this one, cadmium plus nickel oxide plus water. Option number A is the correct answer here. Okay. Next question number 5. Which of the following statements is correct regarding the variations of molar conductivity with concentration? So if you remember, concentration, okay, if decreases, molar conductivity increases, right? So molar conductivity decreases with the decrease in concentration? No. Variation in molar conductivity of weak and strong electrolyte is same? No. So increase, right, molar conductivity in weak electrolyte increases more. Okay. So molar conductivity increases with the decrease in concentration. Yes, this is the correct statement. Next, when concentration of the solution approaches 0, the molar conductivity is known as conductance. No, the molar conductance at that time is called as limiting molar conductivity. Okay. Next, question number 6. Consider the cell. The EMF of the cell can be increased by. Okay. So now if you see, the reaction is like this. Cu gets Cu2 plus, right? So let me write the reaction like this. Your Cu gives Cu2 plus 2 electron, and then you have Ag plus 1 electron, gives you Ag, okay, and multiply 2 here. Now if I add this one, what I'll get? Cu plus 2 Ag plus gives Cu2 plus 2 Ag, right? Okay. So now if you see, what is the Nernst equation for this one? E of the cell will be equal to E naught of the cell minus 0.059 by 2 log of, okay, here I can see log of concentration of Cu2 plus product concentration by remainder concentration or reactant concentration Ag plus square. Now according to the question, copper 2 plus concentration is 10 to the power of minus 2, right? And Ag plus concentration is 10 to the power of minus 1, okay, 10 to the power of minus 1, okay, clear. So for now, this actually this value is log 1 is 0, so this whole value E of the cell is equal to E naught of the cell for this much now. Now if you see, exchanging the constant, the EMF of the cell will be increased by, if we exchange the concentration, even if we exchange the concentration, means they are saying that now the copper 2 plus concentration will be 10 to the power of minus 1 and Ag plus concentration will be equal to 10 to the power of minus 2. So now if that is done, then what we will get here? Here I will get see, here I will get 10 to the power of minus 1 and here it will be 10 to the power of minus 2 to the square. So 10 to the power of minus 4, and here it goes minus 4 plus 10 to the power of plus 3, right? So now we will get a value here. So from E or E naught of the cell, I have to subtract such value, right? So when you subtract some value from E naught of the cell, the value will decrease, right? So that is why this cannot be the answer. Next, decreasing the concentration of the reduction half reaction 10 times. So now if you see the reduction half, so again I will put the original thing what was there here. So we have copper 2 plus and Ag plus square, right? So the reduction half of the reaction is silver. So if the Ag plus concentration is further decreased, right, then what will happen? The overall this value will increase, and when this value will increase, you have to subtract a bigger number from this value. So if you are subtracting a bigger number, what will happen? The value will further decrease, it will anyhow not increase. So that is why this is also not the answer. making the concentrations 1 molar for each side. So if you make 1 molar on both sides, again this one log 1 will become 0 and we will get the same value, it will not increase. Now increasing the concentrations to 10 times in each half cell. So if you are increasing by 10 times in each half cell, let us see what is happening there. So copper 2 plus concentration was before how much? Copper 2 plus concentration is 0.01. Now if you increase by 10 times, it will become 0.1, right? So that will be 10 to the power of minus 1. Okay, and Ag plus concentration was 0.1. If you increase by like 10 times, it will become 1 now, right? 1 square. So now what will happen? This minus 1 will come here, log 10 will become 1. So I will get E naught of the cell plus 0.059 by 2, right? So to the E naught of the cell, some value is added in this case. So if some value will added, then E of the cell will definitely will increase, right? So that is why correct answer is option number D here. Okay, this is a very critical and I can say an actual hot question. Next, a galvanic cell has an electric potential of 1.1 volt. If an opposing potential of 1.1 volt is applied to this cell, what will happen to the cell reaction and the current flowing through the cell? So if you are giving exactly 1.1 volt again, then what will happen? The reaction stops there and no current flows through the cell. Okay, if you give more than 1.1 volt, then the current will flow in opposite direction. Okay, next, which of the following is not correct? Okay, metallic conduction is due to the movement of electrons in the metal. This is correct. The electrolytic conductance is due to the movement of ions in the solution. This is also correct. The current carrying ions are not necessarily discharged at the electrodes. Yes, that is also correct. Okay. The metallic conduction increases with the increase in temperature, whereas that of electrolytic conduction decreases with temperature. Here you have to be careful that for metallic conductor, okay, if you increase the temperature, then the resistance will increase, so the current flow will decrease. So that is why this is incorrect. Option number D is the correct answer. Next, make the correct Nernst equation for the given cell. Okay, so you can see here we have Fe, Fe2 plus, H plus 2, H2. So Fe is getting converted to Fe2 plus 2 electrons, H plus I can write 2H plus 2 electrons give me H2. Okay, so now if I add these reactions, on the product side I will have Fe, on the reactant side I will have H plus. So E is equal to E naught minus 0.059 by 2 log of Fe2 plus, okay, then H2, okay, then I have log of H plus square. Okay, so now if you see here we have Fe2 plus, then that is there, then I have H2, right? So here there is H plus, so we can ignore, here also H plus, here it is H2. Then you have on the this side you have H plus square, so here also H plus square is there. So option number C is the correct answer here. Next, question number 10. The variation of lambda m of acetic acid with square root of concentration is represented by. So if you see acetic acid means CH3, so this is a weak acid, right? So for weak acid what happens? Lambda m increases more, right? So now if you see with decrease in concentration, okay, so now if you see in this side, okay, so you can see one second, the graph is like this: root over of C, root over of C, root over of C, and root over of C. So in this side the concentration is decreasing, right? If you see the concentration is decreasing, molar conductivity is also decreasing. So this is not correct. Here if you see first increase then decrease, this is incorrect. But here if you see concentration when you decrease, molar conductivity is increasing. So that is the correct answer. Option number C here. Okay. Here if you see again concentration, if it is decreasing, like this side, molar conductivity is not increasing, right? Concentration decreasing, molar conductivity is also decreasing, right? Okay, so these are the 1 marker questions that we have discussed. Now we will move towards the 3 marker theory questions. Okay, fine. First question is from the electrochemical cells. What is the role of a salt bridge in connecting anode and cathode or two half cells? So you have to just a very important theory questions. So if you know what is a salt bridge is a U-shaped tube, right? This is a U-shaped tube. So what is the exactly its for like functions? Please remember the answer. You have to, such questions you need to know the answers. First thing, it maintains the electrical neutrality on both sides. Okay. Second, it prevents the accumulation of charges in the half cell. It avoids liquid junction potential. Here you can add one more point. It completes the circuit. Okay, I hope this question is clear. So first is you have oxidation and reduction potential, two half cells are there. It connects that both the half cell and complete the circuit. Second thing is when the reaction proceeds, okay, one side you get more positive ions start accumulating, another side one more negative charge get accumulated, right? So to neutralize that, you need a salt bridge. Next, that is the same thing, it prevents the accumulation of charges in the half cell and it avoids liquid junction potential. Okay. Next, question number 2. What is a salt bridge? What happens when a salt bridge is removed from the electrochemical cell? Why is KCl used in the preparation of salt bridge? So as I told you, what is a salt bridge? It is a U-shaped tube, right? So you can see here, it is a U-shaped glass tube filled with a gel called agar-agar containing KCl or KNO3 or NH4NO3. So there can be an MCQ question here like which of the following is present inside the salt bridge. So you should know it can be KCl or KNO3 or NH4NO3. Okay. Next, the potential drops to 0. So if you remove the salt bridge, there will be no flow of current and the potential will become 0. Now, why only KCl, KNO3 or NH43 is used? Why not other electrolytes can be used? So that is because the mobility of K plus and Cl minus is same. Means the K plus ions can neutralize the negative charge on the left hand side, Cl minus can neutralize the positive charge on the right hand side because their movement is equal, their mobility is equal. So the transport number or the velocity of both K plus and Cl minus are almost same here. Okay. Next, question number 3. What is standard cell potential of the Daniell cell? Write the half cell reaction occurs in the cathode of the Daniell cell. Write the half cell reaction occurs in the anode of the Daniell cell. Okay. So Daniell cell value is 1.1 volt. Okay, the EMF, and here the reaction is like at anode what happens? Okay, I have written here. So at anode, zinc undergoes oxidation, so Zn gives you Zn2 plus 2 electron, and at cathode, copper 2 plus gets reduced, so copper 2 plus 2 electron gives you copper. Okay. Next, question number 4. What happens the cell potential when concentration of the cathodic solution is increased? Mention the direction of the current flow when electrons are moving from anode to cathode during the working of a galvanic cell. Write the symbolic notation of Daniell cell. Okay. So now suppose I have this, like zinc is undergoing oxidation, right? Zn2 plus 2 electrons, and copper is undergoing reduction, okay, to give you copper. Now what will be the final reaction? We'll have Zn plus copper 2 plus, okay, gives you Zn2 plus copper. Now E of the cell will be equal to E naught of the cell minus 0.059 1 by 2 log of Zn2 plus, okay, divided by Cu2 plus. Okay, so this is at anode and this is at cathode. Okay. Now if you increase the concentration of cathodic solution, then what will happen? This overall value will decrease. Now that means, now if you have increased this one, this overall value will decrease. Now you are going to subtract a smaller number from E naught value. Okay, suppose it was earlier you are subtracting x value from E naught, now you will subtract x like something smaller than x. Then obviously, like for example, this value was earlier 5. Okay, so earlier you were doing E naught minus 5. Now what you did, you increase the concentration of copper 2 plus. Cathodic solution means copper 2 plus is there. If you increase the concentration of copper 2 plus, this whole value will decrease, as a result of which this whole value will decrease. Now you are subtracting, suppose E naught minus 3, right? So now tell me whether E here or E here, which one will be greater? If you subtract a bigger number, the final value will be less. Here if you are subtracting a smaller number, the final value will be more. So if you increase the cathodic concentration, E value will increase. Okay, so that is there. So I'll erase all this. Next, direction. Okay, so first one, if the cell potential increases, the direction of the current flow when electrons are moving from anode to cathode. So you know the current direction is always opposite to the flow of the electrons. So if electrons are moving from anode to cathode, current will flow from cathode to anode, right? So that is there. Okay, next you can write down here, it is from cathode to anode. Cathode to anode. Okay, now if you see, the final reaction was like this: Zn plus Cu2 plus gives Zn2 plus Cu, right? So this one to this one is oxidation, and this one to this one is reduction, right? So oxidation half should be written first. So Zn will be oxidized to Zn2 plus. Okay, then you have a salt bridge, and copper 2 plus is reduced to copper. Okay, so here a small error, it is like this. Okay, Zn2 plus to Zn, then copper 2 plus to copper. Okay, this is the answer. Okay, next, explain the function of Daniell cell when, if applied potential is less than 1.1 volt, if applied potential is equal to 1.1 volt, and if the applied potential is more than 1.1 volt. Okay, so if it is applied less than 1.1 volt, then the current will flow as it is. Equal to 1.1 volt, current will stop flowing. Greater than 1.1 volt, it will flow in opposite direction, right? So if applied potential is less than 1.1 volt, it continues to function as a galvanic cell. Electron flows from zinc to rod, zinc rod to the copper rod, and hence the current flows from copper to zinc. This is what happens normally. Sorry, but if it is second one, okay, see, if it is applied potential is equal to 1.1 volt, current stops flowing. Okay, current stops flowing. And the third one, that if the applied potential is, that is E external, is greater than 1.1 volt, then the current will flow in opposite direction. Okay, so current flows in opposite direction. Okay, so now what do you mean by opposite direction? Earlier the current was flowing from, you can see, electron flows from zinc rod to cathode rod, and hence the current flows from copper to zinc. Now the current will flow from zinc to copper. Clear? Okay, let us see the next question. What is electrode potential or single electrode potential? Name the unit to measure the electrode potential. What is standard electrode potential? Now let me explain you first what is electrode potential. So when you have an electrolyte, okay, and a electrode, here we have electrode, okay, and here you have electrolyte. Okay, now what happens, this is suppose zinc sulfate and this is zinc. So now what happens, the electrons comes out of the zinc rod as Zn2 plus. Okay, now Zn2 plus comes out, and here we are left with electrons. Okay, so outside what happens, Zn2 plus are present, and in the rod it is electrons are present. So now what happens, there is a charge difference, because of which there is a potential difference generated, right? So the potential difference generated here is called as electrode potential. Now what is standard electrode potential? Now if, when you measure this electrode potential, if the concentration of this electrolyte is 1 molar, okay, pressure is 1 atm, temperature is 298 Kelvin, when these three things are also maintained, and then also you are measuring the electrode potential, that is called as your standard electrode potential. Okay, so let us see here. The potential developed between the metal rod and its own ions in a solution at equilibrium is called as electrode potential or single electrode potential. Okay. Next, it is, what is the unit to measure it? Volt. Okay. The potential developed between a metal rod and its own ion in a solution at, this is very important, what should be the condition? At 298 Kelvin, 1 molar concentration and at equilibrium is called as standard electrode potential. Now the standard electrode potential is denoted by E naught. Okay, only electrode potential E and standard will be by E naught, like how we use in thermodynamics delta H naught, delta G naught, similarly E naught. Okay. Next question, how does electrode potential changes with concentration? Okay. In a galvanic cell, so now if you see, when you talk about generally electrode potential, we generally talk about reduction potential of electrode. Okay, reduction potential. Now suppose, for example, copper 2+ is there, it undergoes reduction to give you copper. What is the electrode potential of this rod? You will have E naught. Okay, E naught of copper 2+ copper minus 0.059 by N. Okay, 1 second. I need to make some space and write here. Okay, suppose the reaction is like this, Cu2+ plus 2 electron gives you copper, right? This is a reduction reaction. So E of the electrode will be E naught of copper, okay, minus 0.059 by N log of 1 by copper 2+ concentration. Right. Now what happens if you increase, if you change the concentration, or if you increase the concentration? The same thing. Now see, if you are increasing, just now explained, if you increase this value, this overall value becomes less. Now you are subtracting a smaller number from the E naught value, right? So if you are subtracting a smaller value, then E value will increase, right? So that is why the first one is increasing. In the galvanic cell of the following cell reaction, write the symbolic notation of the cell. Okay, you can see copper is undergoing oxidation. So first will be copper, then Ag is undergoing reduction, so it is Ag plus 2 Ag. Now if you want to write the E of the cell, how to write? E of the cell will be equal to E naught of the cell minus 0.0591 by 2 log of. So if you write this reaction separately, copper will give you copper 2+ plus 2 electron and 2 Ag plus 2 electron will give you 2 Ag, right? So on the product side you have Cu2+ and on the reactant side you have Ag+, right? Cu2+ and you have Ag+ square. Okay, this will be the Nernst equation. Clear? Next question. Explain the construction of standard hydrogen electrode or normal hydrogen electrode. You can see how many times these questions have been asked. Next, explain the working principle of SHE. Platinized platinum is used for the construction of SHE. Give reason. Okay, so first let us understand the construction here. Okay, little bit lengthy answer, but yes, very simple. You have to just understand it and you can write this answer in your own words. Okay, so first question is explain the construction. Okay, so SHE is a reference electrode. Okay, because its value is assumed to be 0. Now at this point you do not have to write in the construction part. The standard hydrogen electrode, from here you need to write. The standard hydrogen electrode consists of a platinum foil coated with finely divided platinum. The foil is connected with a platinum wire with mercury. A copper wire is connected from the mercury for external circuit. The platinum foil is dipped in 1 molar HCl solution as shown in the figure. This is the figure. Okay, now let us understand this one. See, you have first 1 molar HCl, then you have a platinum foil. The platinum foil is connected to the platinum wire, okay, and this platinum wire outside is connected in the copper wire, okay. Yes, so that is what is there now. So you can see Once again, let us see. A standard hydrogen electrode consists of a platinum foil. So this is one square is there, that is your platinum foil here, with finely divided platinum. So on that platinum foil you have finely divided platinum particles. The foil is connected with a platinum wire with mercury. So this is connected with this platinum wire to mercury. Okay. Next you have to mercury. Yes, a copper wire is connected from mercury for external circuit. So this external wire which you can see, that is your copper wire. That much you have to write in construction. Next, working of SHE. So what is happening for, how does it work here? So now what we give from this one, we give you pure hydrogen gas. The platinum wire absorbs the hydrogen gas, okay, and then that is dipped in HCl, in which there is a reaction taking place. So you can see here, the pass pure and dry hydrogen gas continuously at 1 bar pressure from the inlet. Okay, this is the inlet. The hydrogen gas adsorbed on the surface of the platinum foil. The adsorbed hydrogen gas is in contact with the H plus ions of 1 molar HCl solution. The electrode reaction is this one. Symbolic notation is given to you. Clear? This is the working. The third one, why we use platinized platinum. Okay, that means that platinum plate is there, on that again finely divided platinum is there. Why? What is the reason for that? So platinized platinum provides more surface area for the adsorption of hydrogen gas. Okay, fine. Next question, how to determine the SRP of copper using SHE. Okay, so this is very simple. One side you have to use hydrogen electrode, another side you have to use copper electrode with copper sulfate solution, connect it with an voltmeter, it will measure the potential difference and give you the value. Okay, so now standard hydrogen electrode is the reference electrode. The given copper electrode is coupled with SHE. Okay, means one side you have copper electrode, one side you have SHE. The EMF of the cell formed is measured using a potentiometer. The measured EMF of the cell, so we have one side H plus, one side copper, corresponding to the equation is 0.34 volt. So that is why SRP of copper is 0.34 volt. So simply you have to write only this much, that it is coupled with this one, then potentiometer measures the EMF of the cell, reaction is what? So my final value is 0.34 volt. Okay. Next, a galvanic cell is constructed using SHE and silver electrode. What is the cell potential? So if you remember, SHE value is 0, assumed to be 0, and silver value is given to you 0.8 volt. So that means 0 and 0.08 volt, so 0.8 volt, so the cell EMF will be 0.8 volt itself. What are inert electrodes? Give an example. Okay, so you can see here, E naught of the cell formula is what? Cathode minus anode, right? So you have E naught of silver minus E naught of H2. E naught of silver is 0.8, H2 is 0, it will give you 0.8 volt. Okay, next, the electrodes which do not, okay, what are inert electrodes? So the electrodes which do not participate in the reaction but provide their surface for oxidation or reduction reactions and for the conduction of electrons are called as inert electrodes. Example, platinum, gold are used as inert electrodes. Now if you see zinc electrode, okay, in ZnSO4, okay, so now Zn comes out as Zn2 plus, right? So now this zinc rod itself is used in the reaction, but if there is an inert electrode, then the rod does not participate, it just provides the surface for the reaction. Okay. Next, question number 11, following are the values of E naught reduction, values of certain elements, arrange them in the decreasing order of their oxidizing power. Okay, this question is incomplete. I'll check this question. Okay, we'll leave this question for now. Let us see the next question. Mention an observation made when an iron rod is dipped into the copper sulfate solution. So if you see, iron rod is dipped into copper sulfate solution. So iron is more reactive than copper. So iron will displace copper and we will get iron sulfate solution and copper will get deposited, right? So that is what you can see here. So observation will what happen? Copper sulfate was blue in color. Now iron sulfate is forming. So the blue color will disappear. So blue color of copper sulfate solution will be discharged due to the reduction of copper 2 plus to copper, and green color will be appeared due to the oxidation of Fe to Fe2 plus. Okay. Given E naught value of nickel is less than E naught of H2, then between nickel and hydrogen, which is more stable reduced form. Now see, which is more stable reduced form. So nickel form is like this, see, Ni2 plus to Ni. Okay, this is the reduced form of nickel, and H plus to H2, this is the reduced form of hydrogen. Now it is saying that nickel reduction value is less, means the conversion for this one to this one is a lesser value, and this conversion is a higher value. Then this one wants to get reduced to H2, means H plus is unstable, so it wants to get reduced to H2. But nickel 2 plus is stable, so it doesn't want to get reduced to Ni. Right. So which reduction, which is more stable in the reduced form? H2 will be more stable in the reduced form. Which of the following is the strongest reducing agent? So just now, just in the MCQ also we discussed this question. Whosever reducing value or reduction potential will be least, that will be the strongest reducing agent. So minus 0.76 is the least value. So zinc has to be the answer here. Okay. Clear? Next, question number 12. Write the Nernst equation for the cell Ni2 plus to Ag plus. Okay. So now we are going towards the Nernst equation question. So you have two questions. You have to write the Nernst equation, then give the relation between EMF of the cell and equilibrium constant. Okay. So first cell, if I write, what is the reaction? Okay, sorry. So if I write here A, Ni to Ni2 plus, right? It is undergoing oxidation, so it will be Ni2 plus 2 electron. Then if I have silver plus 1 electron will give me silver. If I add these two reactions now, okay, I multiply 2 here. Okay. If I add these two reactions, I'll get Ni plus 2 Ag plus gives me Ni2 plus, okay, plus 2 Ag. Right, this is there. Now if I want to write the Nernst equation, okay, E of the cell, so that you have to write the Nernst equation, right? So E of the cell will be E naught of the cell minus 0.0591 by N log of, okay, Ni2 plus whole divided by Ag plus square. Yeah, this will be the equation for this particular thing. Next, if you see option number B, we have Zn giving to Zn2 plus 2 electrons, okay, and you have H plus 2 electron giving you H2. Now if I add these two reactions, what I'll get? Zn plus 2H plus gives Zn2 plus H2. Okay. So now if I want to write the Nernst equation for this one, so E of the cell will be equal to E naught of the cell 0.0591 by 2 log of H2, okay, then Zn2 plus whole divided by H plus square. Okay, this is clear. Okay. Next, give the relation between the standard EMF of the cell and equilibrium constant. So we know at equilibrium E of the cell is 0, so E naught of the cell is equal to 0.059 by N log of K value. Okay, so this is the answer for C question. Okay, clear? Next, question number 13. What are, so we are now going towards conductance, okay. So what are metallic conductors, what are electrolytic conductors, and what are insulators? I think very easy question. So you can see here the conductors which allow the flow of or the movement of electric current due to the movement of electrons are called as metallic conductors. Example, aluminium, copper. Next, the conductors which allow the movement of electric current due to the movement of ions are called as electrolytic conductors. Okay. Example, aqueous solution of NaCl, KCl, etc. Next, insulators, the substances which do not allow the passage of electric current through them are called as insulators. Example, rubber, wood, plastic, wax, etc. Okay. This is important question. Okay. On what factors the electronic conductance or metallic conductance depends? Okay. So, 3 factors you should remember: nature and the structure of the metal that you have taken, number of valence electrons per atom, then temperature. Okay. Next, name the factors on which the conductivity of electrolytic conductor depends, or on what factors the conductance of a solution depends. So, here also you should remember, first is the nature of the electrolyte, whether it is a strong electrolyte or a weak electrolyte. Strong electrolyte means there will be more number of ions, more conductivity of the current will take place, right. Next is temperature. With increase in temperature, it increases. Okay, but here if you remember, one second, for temperature you should remember, if temperature increases, conduction decreases. Okay, for metallic conductor, but for electrolytic conductor it is inversely, like if temperature increases, conduction will also increase. Next is nature of the solvent and its viscosity. So, you have taken an electrolyte, you will dissolve in any solution, right. So, that solution viscosity also matters. Next, concentration of the ions in the solution, size of the ions in their size of the ion and their solvation. Okay. So, you can remember 5 factors here. First is the nature of the electrolyte, next is number of number of ions produced. Okay. Then you have temperature, then you have size of the ions, solvation of the ions. Okay. So, if we talk about size, okay. So, small size, if it is small size, okay, then it is more conduction. Okay, small size means it can conduct more. And talking about solvation, okay, so if more solvation is there, then size increases and less conductivity or less conduction. Okay, clear? Next is question number 16. Give any 3 differences between metallic and electrolytic conductors. Okay, so there are many points, you can write any 3. So, first is the conductivity is due to the movement of electrons, and here it is due to the movement of ions. First and very important thing. Next, they conduct electricity in the solid state, they conduct electricity in the solution state. No chemical decrease with this is important, this point is not required. Okay. Third point, conductivity decreases with the increase in temperature, conductivity increases with the increase in temperature. Okay. Next, here metals do not decompose, but here electrolytes decompose into ions. Okay. Next, you can give no transfer of matter take place, transfer of matters takes place, or you can just give one example here and example here. Okay. So, 4 points you can easily remember. Here it is due to the movement of electrons, due to the movement of ions. Next, the temperature factor, very important. Third point, you can write examples, that's all. Okay. Next, what are electrolytes, what are non-electrolytes? Name the type of electrolytes. Okay. So, we have already discussed what is electrolytic conductors, the same thing are electrolytes. An electrolyte is a substance which conducts electricity either in the fused or molten state or in the solution state, and it decomposes on passing electricity. Okay. So, the electrolytes are those which can conduct electricity in the molten state. Okay. Now, what is non-electrolyte? Opposite of that, right? The substances which do not conduct electricity either in the molten state or in the solution state are called as non-electrolytes. Okay. Non-electrolytes. Example, ethyl alcohol, benzene, glucose, urea, sugar. Type of electrolytes are 2 types, strong electrolytes and weak electrolytes. Okay. Next, what are strong electrolytes? Give example. What are weak electrolytes? Give example. So, strong electrolytes are those which dissociate completely to give ions and can conduct electricity. Weak electrolytes are those which dissociate partially and can conduct electricity, but to the lesser extent. Okay. So, examples, and this one you can see. A strong electrolyte is one which undergoes complete ionization in aqueous solution at moderate concentration. Strong acids examples, strong bases and salt solution are the examples here. A weak electrolyte is one which undergoes partial ionization in aqueous solution at moderate concentration. So examples are like you can give weak acids like acetic acid, weak bases like ammonium hydroxide. Okay, whichever examples you can remember any two examples. Clear? Okay. Next, what is conductance and what is the used unit of resistance in SI unit? Okay. So conductance, if you remember, it was inverse of resistance, right, denoted by G. Okay. The property of the material that allows the movement of electric current is called conductance. Okay. It is the formula denoted by G, or you can say it is the reciprocal of resistance is called as conductance. So G is equal to 1 by R, where R is the resistance. SI unit of resistance is ohm. Okay. Unit of conductance is ohm inverse or Siemens. Next, how is electrical resistance related to length and area of cross section of the object? Define resistivity. What is the unit of resistivity? So here you can see first answer, the electrical resistance of any object is directly proportional to the length and inversely proportional to the cross sectional area. R is equal to rho into L by A, where rho is the resistivity. Next question is about resistivity. So resistivity is the resistance offered when length is 1 meter, area is 1 meter square. Okay. So resistivity of a substance is defined as the resistance of the substance when it is 1 meter long and its cross sectional area is 1 meter square. Next, SI unit of resistivity. So if you see here, just you can find out, no need to remember the SI unit. Rho will be equal to what? RA by L, right? R is ohm, A is meter square, L is meter. So it is ohm meter. Okay, unit will be ohm meter. Next question number 21. What is conductance and give its SI unit? So conductance we have already discussed. SI unit also we have discussed, I think. Reciprocal of resistance gives conductance. SI unit is ohm or Siemens. This is ohm inverse. Okay. Okay. What is specific conductance or conductivity? So conductivity is the reciprocal of resistivity. Okay. So we have two things here. So you can see resistance. Okay, resistance and inverse of resistance. Okay, inverse of R is conductance, resistivity and inverse of resistivity, and inverse of resistivity is conductivity. Okay, so if we have R is equal to rho into L by A, so A into R by L is equal to rho. Now resistivity is 1 by rho, so that means kappa is equal to 1 by rho, that is L by A into R. Okay, so how to define that? So it is the conductivity, means it is the conductance of an electrolytic solution placed between two electrodes of length 1 meter and apart, and the area of the cross section is 1 meter square. Okay, and the unit also it is not asked, but you should know the unit of the conductance or conductivity is S meter inverse or S centimeter inverse. Okay, very very important, unit is S meter inverse. Okay, or S centimeter inverse. Now this kappa is also called as specific conductance, or you can call it as conductivity. Okay, fine. Next, mention the factors on which the conductivity depends. Okay, conductivity means again kappa, right? What is cell constant? So conductivity depends on the nature of the electrolyte, temperature, pressure. Okay, next, what is cell constant? It is the ratio of the distance between the two electrodes L and the area of cross section, that is G. Cell constant is represented by G star and it is equal to L by A. Okay. Next, direct measurement of conductivity of ionic solutions by Wheatstone bridge is not possible. Give reason. Then how do you solve this problem arise in the measurement of conductivity of ionic solutions by using Wheatstone bridge? Okay, so what are the first problems? There are two problems or two solutions. The first problem is the use of alternating current. Okay, so direct current, in the first problem is direct current will change the composition of the ionic mixture during electrolysis. Okay, so we cannot use direct current in the Wheatstone bridge. Second thing, solutions cannot be connected to the bridge like other solid conductor. These are liquid, right? You cannot have two wires and connect a liquid in that. So that is the second problem. What are the solutions? So first solution is using alternating current instead of DC current. And for this one, electrolytic solutions is connected to Wheatstone bridge by using one particular type of cell, and that particular cell is called as conductivity cell. Okay, so you are not using directly the electrolyte, but you are putting the electrolyte inside the conductivity cell and using it. Okay, fine. Next, what is molar conductance? How is it related to concentration and conductivity? Mention its unit. Okay, so molar conductance is the conductance of all the ions produced in the entire solution which contains 1 mole of an electrolyte. So if you take the electrolyte as 1 mole, and in that whatever ions are produced, due to that ion whatever electricity is conducted, that is called as molar conductance. Now how can you relate it? So formula lambda m is equal to kappa by C. Okay, mention its unit. So lambda m is equal to kappa in, so now see, here we have two formula, units are two types. Okay, S centimeter square mole inverse or S meter square mole inverse. Okay, here kappa into 1000 by C. If kappa into 1000 by C, then it is S centimeter square mole inverse. Okay, there's another formula kappa by C into 1000, then it is S meter square mole inverse. Okay, based on in which units you have taken concentration, the formula will change. This formula is widely used, but you should also know about this formula. Okay, next, write the relation between the molar conductivity and molarity of a solution in both SI unit and CJ. So that we have already done. What is the unit of molar conductivity? That also I already discussed. Okay, so unit is S meter square mole inverse or S centimeter square mole inverse. Here if I want to write in SI unit, it is lambda m is equal to kappa into, kappa divided by C into 1000. Okay, and in CGS system, lambda m is equal to kappa into C divided by 1000. Okay, next, what is the effect of dilution on conductivity? What is the effect of dilution on molar conductance? What happens to molar conductivity when 1 mole of KCl is dissolved in 1 liter is diluted to 5 liters? Okay, so conductivity is what? Conductivity is the conductance of the electrolyte per unit volume. Okay, so what happens when you dilute it? Okay, number of ions per unit volume will decrease, so that is why conductivity will decrease. Molar conductivity will increase, and here if you see what happens to the molar conductivity if you are doing dilution, definitely it will increase. Okay, so decreases, increases, increases. Okay, next, this is very important question. Explain the variation of molar conductivity with concentration. So here I am writing point wise. First point you need to write molar conductivity increases on dilution. Okay, second point you have to write for weak electrolytes. Okay, what happens in case of weak electrolytes? So molar conductivity increases for weak electrolytes, okay, due to the increase in dissociation of electrolytes. Okay, next, third one is for the strong electrolyte, what is the case? So for strong electrolyte, the thing is when lambda m, okay, increases for strong electrolyte, okay, due to the increase in mobility. Okay, after this, you know, you have to write one conclusion point, that is molar conductivity in weak electrolytes increases more than in strong electrolytes. Now you have to draw a graph and show. Okay, so this side it is molar conductivity and this side it is concentration. So if you take a weak electrolyte, it will be like this. Okay, so now in weak electrolyte you can see initially the value was this one. Now when you decrease the concentration, the value increased, and this is the value. And next one is strong electrolyte. So if you see in weak electrolyte, this much increase is there, right? And in weak electrolyte, earlier suppose it, in weak electrolyte this much increase is there, but if you have a strong electrolyte, there is only this much increase. So definitely if you decrease the concentration, molar conductivity of weak electrolytes increases more, because when you dilute it, the dissociation increases, more number of ions are produced. Okay, so this is because of weak electrolyte and this is because of strong electrolyte. Clear? Next, define limiting molar conductivity, state Kohlrausch law, give any two applications of Kohlrausch law. So limiting molar conductivity is when you have done infinite dilution, where the concentration is very less. At that time, whatever is the conductivity, molar conductivity of the solution, that is called as limiting molar conductivity. Okay, so you can see here the conductivity of the electrolytic solution at infinite dilution is called as limiting molar conductivity. State Kohlrausch law. So Kohlrausch law states that the molar conductance of an electrolyte at infinite dilution is equal to the sum of the ionic conductances of the respective cations and anions of the electrolyte. So for example, if you have an electrolyte CaCl2, okay, so the molar conductance of CaCl2 is equal to molar conductance of calcium 2 plus 2 times molar conductance of chlorine minus. Okay, give any two applications of Kohlrausch law. So two applications, the first one is it is used to determine the molar conductivity of weak electrolytes, and next one it is used to determine the extent of dissociation. Okay, so how it is used to calculate the extent of dissociation? Alpha is equal to lambda m by lambda naught m. Okay, clear? Next, we'll go towards electrolysis now. Okay, so state Faraday's law of electrolysis and write its mathematical formula. State the Faraday's second law of electrolysis. You can see both of these questions are very repeated question, and please make sure that you remember the definitions properly. Okay, so first question, the first law states that the amount of substance deposited or liberated at any electrode during electrolysis is proportional to the quantity of electricity passed through the electrolyte. M is proportional to Q, where M is the mass deposited, Q is the charge. Now Q can be written as IT, so we can write M is equal to, or M is proportional to IT, and to remove the proportionality you multiplied a constant, that is Z, M is equal to ZIT. Okay, next, Faraday's second law. It states that when same amount of electricity is passed through different electrolytic solutions, the masses of the substances deposited or liberated at the electrodes is directly proportional to their equivalent masses. Mathematical formula for second Faraday's law I'll write here, that is M1 by M2 is equal to E1 by E2. Okay. Next, define electrochemical equivalent and what is the charge of 1 mole of electrons, and define 1 Faraday, what is its value of 1 Faraday. Okay, electrochemical equivalent is Z. Okay, M is equal to ZIT. So it is the, so if I write, see, M is equal to ZIT, or M by I into T is equal to Z. So it is the mass of the substance deposited when 1 ampere of current is passed through an electrolytic solution for 1 second. Okay, that is called electrochemical equivalent. Next, what is the charge of 1 mole of electron? So charge of 1 mole of electrons is 96487, or we can take it as 96500 coulomb. Charge of 1 mole of electron, 96500 coulomb. Define 1 Faraday. What is the value of 1 Faraday? So the charge of 1 mole of electron is called as Faraday, and its value is 96500 coulomb. Okay, so charge of 1 mole of electrons is 1 Faraday, and the value for this in terms of coulomb is 96500. Let us see the next question now. What are the factors that determine the products of electrolysis? Okay, this is very important question. So nature of the electrolyte, type of the electrode used, standard electrode potential of the competing ions, concentration of the electrolytic solution over voltage. Okay, so what are all factors we have studied? Factors on which metallic conductance depends. Okay, factors on which electrolytic conductance depends, right? And one more factor was there, factor on which products of electrolysis depends. Okay, and one more factor question we did, right? Let me check it. Define. Okay, let me see, because we should know, mention the factor on which the conductivity depends. Yes, we have also that question. Okay, so one second. Okay, yes, another, mention the factors on which conductivity depends. So these 4 questions you can write together, because the answers might be confusing, so you should write it and learn it again and again. Okay, these are the factors. Next, what are the products of electrolysis of molten and aqueous NaCl? Okay, so for molten solution, what happens? You get Na at cathode and Cl2 at anode. For aqueous, you get H2 at cathode, Cl2 at anode, and NaOH in the solution. Okay. Next, write the net reactions that occur at anode and cathode and the overall reaction during the electrolysis of aqueous solution of NaCl, and then what is over voltage. Okay, so you have to write the reaction. So NaCl dissociates to give you Na plus and Cl minus, right? Now Na plus is positively charged, so it will move towards, and if because aqueous solution is there, right? Question is for aqueous solution, so you have H plus and OH minus as well, right? So what will happen? OH minus or water will move towards the cathode. It will gain 1 electron, you will get half H2 plus OH minus. Cl minus will move towards the anode, will lose 1 electron, and you will get half Cl2. So the overall reaction is NaCl plus water is Na plus OH minus plus half H2 plus Cl2. Okay. Next question, predict the products of the electrolysis for the following. Aqueous solution of NaCl with graphite rods. So aqueous solution of NaCl. So we will get what? You will get Cl2 at anode, H2 at cathode. Next, aqueous solution of copper sulfate with platinum electrodes. So copper sulfate means what all ions you have? You have Cu2 plus, SO4 2 minus, H plus, and OH minus, right? So you will, out of this copper 2 plus you will get, okay, and you will get out of this one will undergo oxidation, so O2 will go towards the anode, right? O2 is liberated at anode and copper is deposited at cathode. Next, aqueous solution of AgNO3 with silver electrodes. So aqueous solution of AgNO3, so you have Ag, H plus, NO3 minus, and OH minus. Okay, so here what will happen? Ag is having more reduction potential, so Ag reduction of Ag plus to Ag at cathode, and oxidation of silver, okay, because silver electrode is there, so oxidation of silver electrode at silver at anode. Okay, so this is very, very important. Please remember these values, these answers. Okay, so what is that? Because there is silver electrode, right? So here H plus will undergo reduction, but Ag plus, the oxidation of silver electrode to Ag plus at anode. So there is no, these things will not go, the silver electrode itself will undergo oxidation. Next question number 35. Now we are starting the topic battery. So what are primary batteries or primary cells? Give an example, give the uses of dry cell. So primary batteries are those which cannot be recharged. Okay, example are dry cell, or you can have mercury cell. And uses, you can remember any 2 to 3 uses: transistors, clocks, portable radios, tape recorders. Okay. Next, what is anode and cathode of dry cell? What is the electrolyte in dry cell? What is the voltage produced by the dry cell? This is important. Okay, please remember. Anode is zinc, cathode is graphite rod surrounded by MnO2 and carbon. Electrolyte is ammonium chloride and zinc chloride. Voltage produces 1.5 volt. Okay. Next, the same thing you have to mention the for mercury cell, that is anode, cathode, electrolyte and use. So anode is zinc mercury cell and cathode is paste of HgO and carbon. Electrolyte is KOH and ZnO and it is used in hearing aids and watches. Next, what are secondary cells or batteries? You can see how many times this question is repeated. So the cells which can be recharged by passing current in the opposite direction are called as secondary cells or rechargeable cells. Okay. Example, you can give lead storage battery and you can give nickel cadmium cell also as an example. Okay. Next, mention the following for the lead battery: anode, cathode, electrolyte and use. Okay. So anode is lead, cathode is greed. Okay. Greed of lead packed with PbO2. Electrolyte is 38% of H2SO4. It is used in automobiles, inverters and trains. Okay. Next, mention the following for nickel cadmium battery. So nickel, the anode is your solid cadmium, cathode is nickel hydroxide, electrolyte is KOH. Next, what are fuel cells? Give example. How does concentration of sulfuric acid change in a lead storage battery when current is drawn from it? Name the cell which is used in Apollo space program. So fuel cells, if you know what are fuel cells. So the cells which produce electrical energy by the combustion of the fuels like hydrogen, methane, etc. Okay, are called as fuel cells. So generally, if like combustion of some gases has taken place and that combustion energy is converted to electrical energy, such type of cells are called as fuel cells. Okay. Next, how does the concentration of H2SO4 will happen? If the cell is discharging, the H2SO4 concentration will decrease. Next, name the cell which is used in Apollo space program, that is hydrogen oxygen fuel cell. Okay. Next, explain hydrogen oxygen fuel cell. Okay. So this is also very important question. You have to know the construction and working. So first of all, in H2O2 fuel cell, electrical energy produced by the combustion, electron energy is produced by the combustion of hydrogen as a fuel. In the cell, hydrogen and oxygen are bubbled through a pair of carbon electrode into the concentrated NaOH or KOH. So you can see here, you have hydrogen is pumped from this side, oxygen is pumped from this side. Okay, you have anode and you have cathode. Okay. Next, what happens? Catalysts like finely divided platinum or palladium metal are incorporated into the electrodes for increasing the rate of electrode reaction. So you have these rods must have catalyst so that the reaction can take place faster. Okay. Now hydrogen is passed into the anode compartment where it is oxidized and oxygen is passed into the cathode compartment where it is reduced. Okay. This is clear? Okay. Next question, what is rust? Give its formula. Explain corrosion of metals or explain the corrosion is an electrochemical phenomenon. Explain the mechanism of rusting of iron. Okay. So what is rust? So hydrated ferric oxide is called as rust. The chemical composition of rust is Fe2O3.XH2. Now how can you explain that corrosion is an example of corrosion is an electrochemical phenomena? So corrosion takes place by the transfer of electrons, so it is called electrochemical phenomena. Iron undergoes oxidation and acts as an anode here. Okay. Next, explain the methods used to prevent corrosion. Name one metal which can be used as a sacrificial electrode to prevent the rusting of iron. So many methods are there to prevent corrosion. The first, you can write barrier protection. In this you can do painting, greasing, oiling, etc. Then you have sacrificial protection, in which the iron is covered with another metal. Okay. Next you have using anti-rust solutions. Okay. Next, name one metal which can be used as a sacrificial. You can use magnesium, or you can use even zinc here. Okay, these can be used to protect iron. Okay, so now we will move towards numerical questions. Okay, some solve. Now we have done enough theory, and I think if you practice these 44 numerical questions, then definitely you will be able to solve all the questions. Okay, fine. Next, Nernst equation question: calculate the EMF of the cell in which of the following reaction has taken place. Okay, so if I write the reaction, okay, so it is like Ni, sorry, okay, so it is like Ni converted to Ni2 plus 2 electrons. Okay, and you have 2 Ag plus gets 2 electrons to give you 2 Ag. So what is the overall reaction? You have Ni plus 2 Ag plus, it gives you Ni2 plus 2 Ag. Okay. So now if I want to calculate the E of the cell, it will be E naught of the cell minus 0.059 by 2. Okay. N value is 2, log of Ni2 plus divided by Ag plus square. Okay, so if you see here, E naught of the cell is 1.05 minus 0.059 by 2 log of what is Ni2 plus concentration? 0.16, and what is Ag plus concentration? 2 into 10 to the power of minus 3, okay, square. So now if I solve this value, you will be getting around 0.914 volt. Okay, so please check this answer. You will be getting 0.914 volt. Okay, next question. Calculate the equilibrium constant of the reaction. E naught cell is given to you. So equilibrium constant, if you know, E naught of the cell is equal to 0.059 by N log of K, right? So now E naught value is we have 0.46, okay, 0.059 by the N value is 2, right? That is of log of K. So now you can solve this value, take anti-log, and you can find the K value, and K value will be getting around 3.92, okay, into 10 to the power of 15. You can check the calculation and tell if you are getting the same answer or not. So let us see the next question here. The standard electrode potential for Daniell cell is 1.1 volt. Calculate the standard Gibbs free energy for the reaction. So here if you know the formula, okay, so what is the relation between the E of the cell and Gibbs free energy? So delta G is equal to minus NF E naught of the cell, right? So now if I want to substitute, so this, see, if you write this one, this will carry 1 mark. Okay, now for substitution, before that you should know what all the values are given, right? So if I note down the given values here, okay, so that is N value is equal to 2, okay, then we have F value is 96500 coulombs, okay, then E naught value is 1.1 volt minus 2 into 96500 into E naught of the cell is 1.1 volt. Now if you calculate this one, okay, if you substitute this one, you will get 1. Now if you write down the answer with the units, you will get the correct answer. So answer will be 212.271 volt. Okay, you can check the calculation once again, but this one what you will get. Okay, clear? Next, question number 4. Calculate the potential of the hydrogen electrode in contact with a solution whose pH is 10 and the partial pressure of H2 is 1 atm. This is important question because it is an in-text question and it is also not a very easy question, little bit I can say on the tougher side. So now if I want to calculate this one, so first we will write the reduction potential of H plus. So H plus plus 1 electron gives you half H2, right? If I want to write the E of this cell, E of the cell will be equal to E naught minus 0.059 by 2 log of, right, H2 concentration to the power of half divided by H plus concentration, right? Now if I want to substitute here, E of the cell I will calculate, right? E naught of the cell is 0, then I have minus 0.059 by n value, n value I have, this is n value, right? Now you see in this one n value is 1, okay, log of, what is the pressure of H2? 1 atm, so 1 to the power of 1 by 2. Now H plus concentration, if pH is equal to 10, right, then what is, pH is equal to minus log of H plus, right? So if pH is equal to 10, then I can say minus log H plus, right? Minus 10 will come here, okay, that means that is log of H plus, right? So what is the value of H plus here? It will be 10 to the power of minus 10 if you take anti-log on both sides, right? So now if I want to calculate this one, 0.059 log of 10 to the power of minus 10. So minus 10 will go here and will get 0.59 volt. Okay, so the correct answer here will be 0.59 volt. Okay, so this will be plus 0.59. Okay, I think that is correct. 10, oh no, sorry, here it is a small mistake. See, 10 to the power of minus 10, when it goes up it will be plus, right? So you will multiply 10 this side, so it will come minus only because we have this minus. Yeah, so we have this one is minus, this is plus, right? So we'll get 0 minus 0.591. Okay, next question number 5. The cell in which the following reaction occurs has E naught value this much. Calculate the standard Gibbs free energy and the equilibrium constant of the cell reaction. Okay, so first there are two things here. First you need to calculate the Gibbs free energy. Okay, so if you calculate the Gibbs free energy, what it will be? Delta G is equal to minus NF E naught of the cell, right? So that means if you see here, what is the value of F, N value? It will be 2, right? 3 plus 2, 2 plus is 1 electron, but we are using 2 times, so that is N is equal to 2, F is 96500 and E naught of the cell is 0.236. Okay, so now you can solve this and calculate the value of delta G. Now if you want to calculate the equilibrium constant also, for equilibrium constant we have this relation, that is E naught of the cell is equal to 0.059, I'll write it as 0.06 by N log K, right? So now if I solve this, E naught value is how much? 0.236, right? Into this one, if I divide, it will be 0.03, so I'll divide this side, 0.03, okay, is equal to log of K. So now you can take anti-log on both sides and find the value of K. Here you can multiply this and find the value of E naught. Okay, so do this calculation. So this is your K value. Okay, this is the value of K that you will be finding out. Now this one we can multiply here. So just for roughly I am doing it, 200 it will come, 2 5s are 10, 2 6 are 12 plus 1 13, 2 9s are 18 plus 1 19, right? We'll get minus 1300 into 0.236, I'll just writing it 0.24. Okay, so now if I multiply 193 and 0.24, so first 193 into 24. Okay, so I'll get 4 3s are 12, 4 9 36 plus 1 37, so 7, then I'll have 2 3s are 6, 18, 3, so 2 13, then I'll get 16, 4 6 3 2, I'll get 4 6 3 2, and I have 3 zeros. Okay, then I'll put 2 decimals, so I'll get somewhere around this value, that is 46.3 kilojoule. Okay, so you can check this calculation, but this is what you have to substitute. Okay, Next, the electrical resistance of a column of 0.05 mole liter inverse NaOH solution of diameter 1 centimeter. Note down the values here. Diameter 1 centimeter means radius is 0.5 centimeter, right? And length 50 centimeter. Length is 50 centimeter is 5.55 into 10 to the power of 3 ohm. This is your resistance. Next, calculate its resistivity, conductivity and molar conductivity. Okay, so resistivity is what? Rho value, right? Resistivity is rho value. And how to calculate rho? So we know that R is equal to rho into L by A, right? So what is rho? R into A by L, right? So just substitute the values here. So one more thing that you should know here is the A value. What is A value? A is pi, okay, R square means 0.5 square, okay. So the first one to calculate resistivity, this is the value, and what all things we need to substitute? 5.55. So I'll substitute at bottom. Wait. This is like 5.55 into 10 to the power of 3, okay. Next we have 3.14 into 0.5 square divided by L is 50 centimeter, okay. So now if you solve this, you will get the value for resistivity. Now conductivity, how to find? Conductivity will be 1 by resistivity. So whatever values we have got here, we have to just reverse it. So I can write like this: 50 divided by, okay, 5.55 into 10 to the power of 3, okay, then into 3.14 into 0.5 square, okay. Next we have molar conductivity. So once you have found this one, molar conductivity formula is kappa, okay, and you can see since it is in centimeter, the formula will be kappa into 1000, okay, by C. So now I can substitute the kappa value is 50 by 5.55 into 10 to the power of 3 into 3.14 into 0.5 square, okay, into 1000, okay, into C. So what is the concentration here? 0.05. So one second. So that is 0.05. Okay, so I have substituted the values. You can check here. Okay, any doubt, please see. So this is kappa value. Just I have written whatever I have written here. I haven't solved it. Kappa. Then this 1000 is there, and this is the C. Okay, so now if I solve all these questions, that is resistivity, and here it is conductivity, and here it is molar conductivity. If I solve this, the answers that I will be getting is, okay, I have written only kappa value. Okay, other things you can just calculate and find the answer. Okay, just everything is substituted. Make sure that you do the correct calculation. Okay, and please comment down the answers for these questions. Okay, next question. Okay, we have kappa value, molar conductivity value, and we have resistivity value as well. So I have written all the answers. So let me write it down in box. So this one, if you calculate, okay, finally you will be getting around 87.135 S centimeter inverse. Okay, then we have, sorry, not S centimeter inverse, S meter you will get, S centimeter. I will correct the units here. Okay, this is, you will get ohm meter. Okay, next if I calculate this one, that is conductivity, kappa value is 0.01148 S centimeter inverse. Now lambda m value will be 229.6. Okay, that is S centimeter square mole inverse. Clear? Next, question number 7. Calculate the lambda naught m for CaCl2 and MgSO4 given that the values are given to you. Okay, so you need to calculate for lambda m for CaCl2. Okay, so that will be what? Lambda naught m, okay, of Ca2 plus 2 times lambda naught m of Cl minus. Okay, so lambda naught m of calcium 2 plus is 119, okay, plus 2 times of Cl minus is 76.3. Okay, so now it is 119 plus 2 3s are 6, 2 6 are 12, 2 7s are 14 plus 1 15. Okay, so now if I add this one, 119, 152.6 plus 119. Okay, so it is I'll get 271.6. Okay, and S centimeter square mole inverse. Do not forget to write the units. Okay, that is the first one. Next one is to calculate for another MgSO4, right? So that is direct. You just need to add lambda naught of MgSO4 is equal to lambda naught of Mg2 plus lambda naught of SO4 2 minus. Okay, so Mg2 plus value is 106 and this is 160. So 106 plus 160. Okay, S centimeter square mole inverse. Okay, so now if I add this is, I'll get 6 plus 06, 6 plus 06, 266 S centimeter square mole inverse. Okay, so we have two answers. This is one answer. Okay, and this is another answer. Clear? So I have written you only this one. This one is also there. Okay, next question number 8. The conductivity of 0.001028 mole liter inverse acetic acid is this much. So conductivity, so first let me write down the data. Concentration given to me is 0.001028 mole liter inverse. Then conductivity means kappa value given to me is 4.95 into 10 to the power of minus 5 S centimeter inverse. Calculates its dissociation constant if lambda naught m for acetic acid is 390.5 S centimeter square mole inverse. Okay, so what is the value? We need to calculate dissociation constant. Alpha formula is lambda m by lambda naught m, right? So we are given with lambda naught m value which is 390.5, right? S centimeter square mole inverse, that is 390.5 is already there. You need to find lambda m. So what is the formula to calculate lambda m? Kappa into 1000 by C, right? So what is kappa value? Kappa value is 4.95 into 10 to the power of minus 5, 1000 is 10 to the power of C, and concentration is 0.001028. Okay, so now whatever value I get, I have to substitute here, and lambda naught m value is also already given, so I can write alpha will be equal to this value. I am substituting 4.95 into 10 to the power of minus 5 into 10 to the power of 3 whole divided by 0.001028. Okay, into lambda value is 390.5. Okay, so now if you substitute this and calculate, you will be getting around 1.78 into 10 to the power of minus 5. Okay, so please check this calculation, you will be getting this value. Okay, next is question number 9. Conductivity of a 0.00241 m acetic acid is given to us. So let us write down this value. Conductivity of, so first concentration is 0.00241 m. Okay, acetic acid conductivity value means kappa value is given to me 7.86 to 10 to the power of minus 5 S centimeter inverse. Next, calculate its molar conductivity. Okay, if lambda m for acetic acid, okay, lambda m is given, okay, lambda naught m is again 390.5. Okay, you have to calculate first the molar conductivity and then the dissociation constant. So very similar to the previous question, right? So if I first calculate molar conductivity, it is kappa into 1000, 7.896 into 10 to the power of minus 5 kappa into 1000. So first we should write the formula, right? Okay, so one second. So lambda m is equal to kappa into 1000 by C, right? This is the formula. That implies here lambda m is equal to 7.896 into 10 to the power of minus 5, that is kappa value, into 1000. Then divided by concentration is 0.00241. Okay, now this is your lambda value. Then now if you want to calculate alpha value, it will be lambda m by lambda naught m, right? So what is lambda m value here? This is 7.896 into 10 to the power of minus 5 into 10 to the power of 3 divided by 0.00241. Okay, that is there, into what is lambda naught value? 390.5. Okay, so now if I solve this, you will be getting 1.86 into 10 to the power of minus 5. Okay, so you can solve this, you will get into 10 to the power of minus 5. Okay, so this also you can check the calculation and get the answer. Okay. Next, solution of copper sulfate is electrolyzed for 10 minutes. Okay, time given is 10 minutes. Okay, with a current of 1.5 ampere. Okay, what is the mass of copper deposited at the cathode? You have to find the mass of copper deposited at cathode. The atomic mass of copper is given. Okay, so we have the formula for that, Faraday's first law, F is equal to Z into I into T. What is Z formula? Z is molar mass, okay, divided by N into 96500, okay, into I into T. So now what is molar mass here? 63.5. Copper molar mass is 63.5 into, Now if copper is deposited, what reaction takes place there? You have seen Cu2 plus 2 electron gives you copper, right? So what is the N value? N value is 2, right? So this is 2 into 96500 into I value is 1.5 ampere. Okay, now time is 10 minutes and 1 minute is 60 seconds, so time should always be in seconds. So please remember, whenever you are using Faraday's law, the time value should be in seconds. Okay, so now if you solve this, you will be getting around 0.2938 gram. Okay, so just check the calculation, this value should be the answer. Okay. Next, if a current of 0.5 ampere if a current of 0.5 ampere flows through a metallic wire for 2 hours, okay, so time I is equal to 0.5 ampere and current is 2 hours, okay, then how many electrons would flow through the wire? Okay, how many electrons should flow through the wire? So now, if you remember, okay, 96500 coulomb is the charge of 1 mole of electrons, or I can say this much coulomb is 6.022 into 10 to the power of 23 electrons. If they will flow, this much charge they will carry. Now, so if I say Q here is equal to I into T, or I can say 0.5 into 2 into 60 into 60. Right? So this is the total charge. Okay. So now here I can say that 96500 coulombs gives how many electrons? 6.022 into 10 to the power of 23 electrons. 1 coulomb will be how many electrons? 6.022 into 10 to the power of 23 divided by 96500. Next we have how much coulombs? This much coulombs, right? So 0.5 into 2 into 60 into 60 will be equal to this, divide this into this much coulombs. So 6.022 into 10 to the power of 20. So let me write it down. So students, after I complete, I'll be aside, you can see that. So please just wait for 1 minute. So 6.022 into 10 to the power of 23 divided by 96500. This was the charge carried by 1 coulomb. This was the number of electrons carrying 1 coulomb of charge. For carrying this much coulomb of charge, I need 0.5 into 2 into 60 into 60. Okay. So now if I solve this, you will be getting around 2.25 into 10 to the power of 22 electrons. Okay. Clear? So first you should know, for solving this question, you should be having the idea of this concept that 1 mole of electrons, or 6.022 into 10 to the power of 23 electrons carry 96500 coulombs. Okay, fine. Next, question number 12. Consider the reaction how many coulombs are needed to reduce 1 mole of Cr2O7 2 minus. Okay, so if you have Cr, okay, if you have Cr2O7 2 minus gives 2 Cr3 plus. Okay, then from plus 6 to plus 3 we have 6 moles of electrons. Okay, so now how many, consider the reaction and the question for 1 mole of Cr2O7 how many coulombs are needed. So if you see, to convert 1 mole of Cr2O7 we need 6 moles of electrons. Okay, and 1 mole of electron is how much coulomb? 96500 coulombs, right? So 6 moles will be equal to 6 into 96500 coulombs. So if I multiply, I'll get 600, 600, 6 5 is 33, 6 6 is 36 plus 3 39, 6 9 is 54 plus 3 57,900 coulombs. Okay, so yes, now if you take this value slightly different, this answer will be, because sometimes we take 96487 something, but 96500 is a standard value, you can take it. Okay, next, how many charge is required to reduce? Okay, charge is required. How much charge? Al3 plus to Al. So it requires 3 Faraday, right? Because you can see the reaction, Al plus 3 will gain 3 electrons to give you Al, right? So 3 Faraday. Next, 1 mole of MnO4 minus to Mn2 plus. So if you see MnO4 minus to Mn2 plus, so this is plus 7 to plus 2, right? So this one will give you 5 electrons or 5 Faraday. Okay, next one, Cu2 plus to Cu 2 Faraday. But if you want to calculate in terms of coulomb, so it is 3 into 96500, then 5 into 96500, then 2 into 96500. Okay, so if I write this one, 3 5s are 15, 1 3 6 are 18 plus 1 19, 3 9s are 27 plus 1 28. If I multiply 5, so it is 500, 5 5s are 25, 2 5 6 are 30, 32, 3 5 9s are 45 plus 3 48. Now this one will be 193000. Okay, so you can see these are the values for this particular question. Okay, next, this is important question from Faraday's second law. Okay, 3 electrolytes A, B and C containing the electrolyte ZnSO4, AgNO3 and copper sulfate respectively were connected in series. A current of 1.5 ampere was passed through it until 1.45 gram of silver were deposited at the cathode of cell B. Okay, so we have current of 1.5 ampere. Okay, mass of silver deposited is 1.45 gram. How long did the current flow? How long did the current flow? First you have to find this one. Okay, okay. Next, what mass of copper and zinc were deposited? Okay. Atomic mass of copper is 63.5, zinc is 65.3 and Ag is 108. Okay, so if you remember, I will solve this question. Okay, how much current flow, but before that, if I know that mass of copper deposited by mass of silver deposited is equal to the equivalent weight of copper by equivalent weight of silver, right? So if I substitute this one, okay, so I am doing the second part of the question first. So mass of copper deposited we need to find out. Okay, then mass of silver deposited is 1.45. Okay, then equivalent weight. So how to calculate equivalent weight? Equivalent weight is molar mass divided by n factor, right? So now equivalent weight is equal to molar mass divided by n factor. So copper equivalent weight is 63.5 divided by 2, right? 63.5 divided by 2. And what is the equivalent weight of silver? 108 divided by 1. Now if I solve this, so m of Cu is equal to 63.5, okay, divided by 2 into 108 into 1.45. Okay, So now if I solve this calculation, I'll be getting, so on solving this, I'll be getting 0.426 grams. Okay. Now we want to calculate the mass of zinc deposited, right? So same thing I'll do, mass of zinc by mass of silver, okay, is equal to equivalent weight of zinc divided by equivalent weight of silver. Okay. So now if I substitute mass of zinc, okay, divided by mass of silver is how much? 1.45. Okay, I hope this is visible. Next, equivalent weight of zinc is molar mass by n factor. So for copper I have taken n factor is 2. Why? Because copper 2 plus gets deposited like this, right? Cu 2 plus 2 electron gives you copper. Okay. Similarly, Zn 2 plus 2 electron, it will give you Zn. So what is the mass of zinc here? 65.3. So we will have 65.3 divided by 2 into the equivalent weight of silver, that is 108. For silver, what is the reaction? Number of electrons required is 1 only. So that is this value. So if I want to calculate this one, so this I will multiply on this side. So how much I will be getting here? Now if I solve this calculation, I will be getting 0.438. Okay, so the mass deposited will be 0.438. Now another part of the question is left, that is how long did the current flow. So to calculate this one, if you know, we have the formula M is equal to Z into I into T, right? So I will just substitute the values here. Okay, so let me solve in this small space. So T value will be M by Z, M divided by Z into I. So mass deposited of copper was how much? Sorry, silver was 1.45. Right, 1.45 divided by Z is equal to molar mass, right? What is the value of Z? Z is equal to molar mass divided by N into 96500, right? So I can write the molar mass here is 108, molar mass divided by N into 96500. Okay, Z is there, I value I have to substitute. So I am erasing this now, okay, because I am having little space constraint here. So I value is how much? 1.5. Okay, now time is given to me as we have to calculate the time, right? This is, so T will be equal to M divided by Z into I. Okay, so I have written this one wrong. Current will be in the denominator, right? Clear here? T will be M divided by Z into I. M was 1.45. Z is molar mass divided by N into 96500. Molar mass is 108. This N into 96500 will go above. N is equal to 1 and 96500. And then I have I as 1.5 ampere. So now if I solve this, okay, so if you solve this now, the value that we will be getting for the time which the current flew was how much seconds we can calculate. So you will be getting an answer of 863.7 seconds. Okay, fine. Next, question number 15. How much electricity in terms of Faraday is required to produce 20 gram of calcium from CaCl2? Okay, so now if you see, you want to produce how much electricity in terms of Faraday is required. Okay, so now see, calcium 2 plus, okay, 20 gram, Ca2 plus 2 electrons gives you Ca, right? This is 40 gram. Okay, so what I can say is, see, for 2 Faraday if required, that will deposit 40 grams, right? So for 20 grams, how much Faraday will be required? Half of this one, so that is 1 Faraday. Okay, next, 40 gram of aluminium from molten Al2O3. So now if you see the second part, okay, Al plus 3 electrons gives you Al, right? So I can say that 3 Faraday deposits 27 gram is deposited by 3 Faraday, right? So 40 gram will be deposited by, so 1 gram will be deposited by 3 by 27 and 40 gram will be deposited by 3 by 27 into 40 Faraday. Okay, so now if you solve this, you will be getting 1 Faraday and this one will be 4.44 Faraday. Okay, now let us go to the last question. This is important question again. Okay, an electric current of 100 ampere. Okay, so what is the I value? I value is 100 ampere. Is passed through a molten sodium chloride solution for 5 hours. Okay, calculate the volume of chlorine gas liberated at electrode at STP. Okay, so if I write chlorine formula, the reduction of chlorine, okay, it will be, right, so I can say that 2 Faraday, okay, let me write it in one form like this, 1 second. Okay, 1 second, yeah, so I can say that this is half mole, right, and 1 Faraday deposits half mole, right. Now if you convert this half mole to volume, you know 1 mole occupies 22.4 liter, so half mole will occupy half of this one, 11.2 liter, right. So I can say that in 1 Faraday 1.2 mole or 11.2 liter will be collected or will be produced. Now if you see in this much, how much coulomb is there? Q is equal to 5 into 60 into 60, okay, I is 100, okay, so we have I into T, T should be in seconds, so 5 6 are 30, so I'll just multiply, there are so many zeros here, so 5 6 are 30, 30 into 6 is 180, so these 3 numbers if I multiplied, I'll get 180. Apart from that, 1 2 3 4 zeros are there, right, so I can say 18 lakhs. So 1 Faraday is giving you this much liter, so 18 lakh Faraday, sorry, this is 18 lakh coulombs, right. Now that means how much Faraday, or I can say like this here, 96500 coulombs. 1 Faraday is this much coulombs, giving you 11.2 liter. So now if I have this one, 18 lakhs coulomb will deposit 11.2 divided by 96500 into 18 lakhs liter. Okay, so now if I solve this, you will be getting 208.91 liter. Clear? Okay, fine. So now coming to the most important topics that you should revise from this chapter. Okay, so that is first of all Nernst equation, numericals you must practice, Faraday's law definitions, both the law and the numericals, Kohlrausch law definition, conductance, there are so many formulas here, so you should be very particular about this. Then Gibbs free energy and equilibrium constant relation, galvanic cell diagram and all you should know, and about the products of electrolysis. Okay, these are the most important topics that you need to cover from this particular chapter. Okay, so 1 second. Okay, so once again I want to remind you about the PU2 success blueprint test series. So this is a test series launched by Diksha to help you to get 95% and above in your PU2 examination, and in this test series there are 12 mock tests which includes 4 part tests and 8 full length papers based on the subject physics, chemistry, maths, bio or CS, and the question papers will be according to the latter syllabus and pattern. Apart from this, you will also be getting the one-shot revision videos, you will be getting the video solutions with detailed explanation, and all your doubts will be clarified on these topics, okay, on these mock tests. And all these you can avail at a discounted price of just 599 rupees. So students, if you are aiming for 95% and above in your PU examination, so please do not skip this, do not take it lightly. Please go, registration link is there in the description section. Go there and buy the test series as soon as possible, because the first test of this test series will be released on this Sunday, that is will be released on 15th of December. Okay, Clear. So yes students, that's there. So I hope all of you will join this, and then that's all in this class. Thank you for watching, and I told you whatever questions I have done in this particular lecture, if you practice all those questions, then you do not have to refer any other source for this particular chapter. Just do these 50-60 questions, then you are done for this chapter. Okay, so thank you for watching students, and see you soon in the next class.